Hello, it's Keith here, and this is lesson 2 of my 6809 assembly programming tutorials. We're going to be looking at the addressing modes of the 6809 this week, and it's going to be quite long because there's an awful lot of them. The 6809 is basically an extension of the 6502 kind of way of doing things, but they've added a lot of extra stuff, and so we're going to go over all of them today. Let's go over to today's code and let's see what we're going to be looking at. So we've got this example file here, and we've got all these different sections which contain addressing mode examples, and we're going to go through them one by one. We're going to see each addressing mode working, and we're going to learn what it means. Okay, so first of all, we're going to run these ones here. Now, these are the simple ones. Let's just fire this up, and then we'll discuss each one of them. Now, there's a few addressing modes combined into this simple example because they were very basic and they didn't really warrant examples of their own. Now the first one is inherent addressing, and this is where the command itself defines what the parameter is going to come from. So in this case you can see that the A accumulator is in the inc command itself. Now in the example here you can see we had 78 in the accumulator, we added 1 and it's gone up to 79 here. The accumulator is the top part of the double accumulator, of course. So that's how we do that with inc A, and of course we could use inc B as well if we preferred. Now the next one is register addressing. This is where the parameters is a register. In this case we're transferring from register A to register B here, and you can see that that has happened here. The 79 has been copied from the top half of D, the A part, to the bottom half, the B part here. So that's the register addressing because the parameters are registers. Immediate addressing is where the parameter is actually in line of the code itself. You see here this 1f is an immediate value defined by this hash symbol here, and that means the value for the load A command in this case is this immediate value. Now in a lot of the cases we're looking at here, these kind of parameters can be used with other commands, of course. I'm just using one example to show the addressing mode in use, and I'm using a very simple one in this case of an LDA. So here we're loading 1f. This dollar symbol defines hexadecimal, of course, hopefully you know that, and so that's those examples there. So those are the simple examples. Next, let's move on and let's have a look at the direct page examples. Now the direct page is what used to be on the 6502 the 0 page, but the 0 page always started with the top byte 00 and then the bottom byte was the 0 page in position. But in the case of the 6809, the page doesn't need to be a 0. The top byte is defined by the DP register, so we don't call it 0 page, we call it direct page. But if you're familiar with 6502, then it's to all intents and purposes the same, and it is at 0 in our case. Okay, let's fire this example up and let's see what happens then. So you can see in this example we've loaded from address hexadecimal 80 in the direct page here, and we've loaded into the accumulator. Now the accumulator is of course this top half of D here, and address 80 you can see just here is 11 in hexadecimal. So when we've loaded in, the top half has become 11 here because of that load in. Now in that case we've loaded in directly from the direct page, but we may want to load in from an address in the direct page, and this is known as indirect direct page addressing. Now on the 6809 we specify square brackets to define that the address here in the 0 page is not the source of the parameter, but it's the address at that address that is the source of the parameter. Okay, so if I enable some more of the code here, just going to show another memory range here just so we can see the effect of the example here. So first we loaded in from the direct page at hexadecimal 80 here, the 11 into here. Next what we did is we loaded indirectly from address 81 in hexadecimal. Now 81, the two consecutive bytes are 12, 13 here, and of course we're using 2 bytes because it's a 16-bit address bus, and that's implied by this command here. So this indirection of 81 will load in 81 and 82, and they will become the address we load in from. Now the 6809 is a big endian system, so we're loading in from 12, 13, and that's, you can see this memory range here, so that's 10, 11, 12, 13, this 42 here, and that value has been loaded in to our accumulator here. So that's how indirection works. It loads in from a 16-bit address at the direct page address we specified, and we specify indirection with these square brackets here. Okay, so that's our basic direct page examples. Now next we're going to look at extended addressing. Now extended addressing sounds a bit sort of over dramatic, but it's actually very straightforward. I do need a different memory address range for this example though. I'll just enable that one. Now instead of specifying a direct page entry, we can actually, of course, specify a full 16-bit address that we want to read from. So in this case, we have specified that we want to load in from memory address 2000 directly. So memory address 2000 you can see here, and that address is a 1A. So when we've loaded in, we've loaded our 1A into the accumulator here. Now we can also load in indirectly. So in this case, we've loaded indirectly from the memory address 2000. So that's taken the memory address 1A, 1B here and loaded in from that. I don't have that shown, so we'll just need to show that. Here we go. So we've loaded in from indirect address 2000. Memory address 2000, we've got 1A, 1B. And here we have 18. So this is 18, 19, 1A, 1B. So that address here in big endian again is this address here. And that's the parameter that's been loaded in. So you can see the indirect extended address is the 16-bit address, and we've indirectly loaded from that. And you'll notice at this point that the 6809 compared to the 6502 has a lot more flexibility with its addressing modes, that we can do a lot of different indirection, and we can use offset registers very differently. There are only very few addressing modes available to us on the 6502. The 6809 has a lot, an awful lot, but it does mean the code is bigger, unfortunately. Okay, so that's the extended. Next we're going to have a look at indexed. Let's give that a go. Okay, so we're going to look at indexed addressing here. So we're going to be using the indexing registers. Now these are Y, X and the two stack pointers S and U. Now we're not going to look at S here because it's a little bit difficult to work with, because of course it's changing all the time, but we are going to look at U and we're going to have a go with that. Okay, let's fire this example up and let's see what happens. Okay, so what we've done here is we've loaded Y with hexadecimal 2000, you can see that here. We've also loaded U with 2002 here, and we've shown the monitors to the screen. It's not actually showing the U register here, so you just have to take my word for it. Then what we've done is we've loaded in A from the Y register. Now we've not specified any offset here, but we do have this comma just for clarity. Now usually what we'd do is we'd specify an offset, either positive or negative from the register, but we can specify no register offset. We could of course specify 0 as well, that would work fine. Here we're going to be loading in A from the address in the Y register here. Well, the Y register contains 2000, so A has loaded in from 2000, which is 1A. Now next we've loaded B from Y plus 1, the 1 specified before the comma here. So that will load in from 2001, 1B, and you can see that has loaded in just here. Next what we've done is we've loaded in X, offset U plus 2 here. Well, U contained 2002, so it was pointed to here, and then plus 2 means it's pointing to just here. So that's loaded in 1E, 1F here, because that's a 16-bit register here. And then we've loaded in Y from U minus 1. Well, U was pointing here, and so minus 1 will point to here, and it's a 16-bit register, so we've loaded in 1B, 1C from here and here. Okay, now these offsets can be used with fixed values, as you can see here. We can also use a symbol. In this case we've defined test off, and we've set that to hexadecimal 80, and we can use that as well. And like with the extended addressing before, where we could use 16-bit values, the 6809 allows 16-bit values with an offset here. So in this case we're loading in from hexadecimal 2000 offset from Y here. So that's a very big offset indeed, and that has had the effect of loading in from 2002 here. And so B has loaded in 1C just here. As I say, all of these are just examples of the ways that 6809 really gives us a lot of power if we're familiar with the 6502. Unfortunately though, all of these extended addressing modes, they do extend out beyond a single byte command when they're compiled to code, so you are sacrificing some speed there, but as I say, the flexibility is definitely very impressive. Now just to make the point, we did sort of briefly look at it there, but the offsets we don't have to specify, so all of these are 3 equivalent versions of the same addressing mode. They're all technically an offset from an indexed register, just like these here, but they are ways that we can just use the Y register on its own. So we can specify comma Y here with no value specified. We can specify 0 comma Y, and we can also specify just Y on its own here. And you can see here, these have all loaded in the same value. This one's loaded in a 16-bit value here. So you can see that's worked just fine. Now, as well, just a sort of technical thing, the way that the commands compile, of course the assembler is doing all the work for us, but the size of the command will vary depending on the size of the offset. So a very large offset like this one here will compile to, I think that's going to be 3 bytes, the parameter for that one. But if we can manage to keep our offsets very small within a 5-bit range, these will compile to much smaller commands. And if I just run these here, you can see these examples here of an offset of -2, -1, 1 and 2 here. So you can see here we're just loading in some test examples here. So here you can see we've loaded in 1C and 1D with our -2 and our -1. And then we've loaded in 20 and 21 with our +2 and our +1 here. And as I say, if we use smaller offsets, these will actually compile to smaller commands. Now, next we're going to look at program counter relative addressing. Now, this is going to be one I don't think you're going to need very often. Now, this is where we specify a label and we specify PCR, which stands for Program Counter Register. I believe this is used for relocatable code, but as I say, in general, I don't think you're going to need it very often. In this case, what we're doing is we're loading in from test label, and of course the offset to test label will be calculated, and we're specifying it as an offset from the Program Counter Register here. And if I just compile this here, well, in this case, obviously, we've loaded in FEDC here. Now, there is another addressing mode called constant offset from program counter. However, I couldn't get this to work in a practical way. I've seen it documented in the books, but maybe I was using it wrong in some way. But we won't be able to show that one in action today, unfortunately. Okay, let's take a look at indirect with constant offset addressing here. So this is where we're using the indirection, and we're also using an offset again. So this is where we're using a register and also an offset, and we're using the address at that resulting value as the source for our command. Okay, let's fire this one up and let's see it in action. Okay, so what are we doing here? Well, what we've done here is we've loaded in from memory address 80 offset by 1, and we've used that as the source address for the parameter here. So in this case, address 80 plus 1 is 1213, and I don't have that on screen. Okay, well, let's fix that. Hang on a minute. Okay, so we've loaded in from 80 plus 1, 1213 here. So that's 1210, 11, 1213 here. So we've loaded in address from this address here, value 42, and you can see that 42 has been loaded into A here. Now after that, we've used an extended value here, this 16-bit value here. So we've loaded in from address 2000 offset by X, and X of course being 1 again. So here's 2000. So we're going to load in from 1B, 1C here. And again, I haven't got that on screen. Just a sec, let's load that in as well. Need to show all of these test values here. 1B, 18 here, let's show that. Okay, so 1B, 1C, so this is 1B, 18 here, 9A, B, C. So here's this value AB, and so we've loaded in that because at the address we specified 2000 plus 1, the 16-bit value is 1B, 1C, and that is the address that the parameter is loaded in from in our command here, loading into B. Okay, now in those examples we've used fixed values, but the 6809 goes far further than that. We can actually use an accumulator as an offset from a base register. So with YX and the stack pointers, we can actually use A or B, the 8-bit accumulators here, and we can offset using those. So that's what we've done here. Now, of course, this is going to be great for your kind of loops where you're reading in data and things. So here in this case, we've loaded X with 2000 again, and we've loaded A with 4 and B with 5. And so we've loaded in from A, X here, which is the equivalent of 4, X, and this is the equivalent of 5, X. So here is our values here. So here's 2000, and you can see 1, 2, 3, 4 here. So this is the address we're loading from, and we're loading into Y. So Y has become 1E, 1F here. And then after that, we loaded D with B from X. And in this case, we have loaded in from 2001, 2, 3, 4, 5 here. So we've loaded in 5 and 6 here, these ones here, 1F20, and we've loaded that into here. Now, it is important to point out that we can also use the 16-bit accumulator in these examples here. I have no idea what that's going to load in, but it will compile just fine. So we have the option of using A, B, or even the 16-bit D accumulator here in these commands. So they're very, very powerful indeed. Now, the next thing possibly won't surprise you. In those examples we've used the sort of direct addresses, but like with the other commands, we can use indirect addressing as well. So you can see here we've got some square brackets here. So in this case we've loaded in from the indirect address hexadecimal 80 plus 1. So that would be 1213 here. 1210 is here. 11, 12, 13. So this value is 4243, and that 16-bit value has been loaded into the Y accumulator just here. After that, we then loaded in the D accumulator from the value in X plus B, which is 2. So of course this would be 1, 2, 1, 3, 1, 4 here, and I haven't got that on screen. Let's just get that on screen here. So we've loaded in from a hexadecimal 80 plus 2. That's 0, 1, 2, 1, 3, 1, 4 here. So this is 0, 1, 2, 3, 4. So this is 1314 here, this 16-bit value, 33, 34, and you can see that's been loaded into the D accumulator here. And so again, we've got a lot of flexibility here, and again, we can also use the D accumulator if we prefer. It will compile just fine, although who knows what it's loaded in. It's loaded in 286 from somewhere for some reason. Okay, so that's the addressing modes using the offsets and using the base registers. Now we're going to look at some more sort of classic ones now. We're going to look at auto increment, which is going to be something I'm sure you're familiar with if you've done assembly on other systems. Now the 6809 once again gives us more power than you would expect from most systems. We can increment by 1 or we can increment by 2, so great for reading 16-bit values, I guess. Okay, let's just fire that up and let's have a look. So in this case, we've got the X register here, and the X register is being used as the source address to read into A here, but we're also incrementing X by 1 each time. We're also going to read in from Y into B, but we're going to increment that by 2, and we're setting X and Y both to 80 to start with, so this is this range here. And so you can see here that the first time we're loading in X from this value here, 11, and then of course it goes up by 1, reads in from 12, 13, 14, 15, so on. Now the bottom half, the B part here, we're loading in from Y, which you can see is going up by 2 each time, and so that's reading in 11, 13, 15, 17, you can see here. So the increment occurs after the read. That's of course why the plus is appearing at the end of the register, and we can increment by 1 or by 2 for our registers as we read from the address contained within them. So very handy there. And we do have a matching decrement command, of course. So as in most assembly languages, the minuses now appear before the command and the decrement occurs before the read. Let's just fire these up and you'll see the entire opposite. So we're setting X and Y to 84 and 88 here, so we're reading from the end of these ranges here. So you can see here we've loaded in 14, 13, 12, 11 as the X register's gone down, and the Y register's gone down by 2 again, and you can see we've loaded in 17, 15, 13 and 11 here from these values just here. Very good. Of course, in those cases we were reading from the address contained in those registers, but once again we have indirection, we have an indirect auto inc and an indirect auto decrement. Let's just see those in action. So again, we're loading in from the direct page entries here. We specify those in X and Y, and this time we're going to be loading in from these addresses. So first we've loaded in from 1112 here, and that is just here, and so that's loaded in 0. Actually, wasn't much point showing that. And then what we've done is we've incremented X and we've read in again. So this time we're loading in from 1213, and that is just over here. So it's loaded in this 42 here, and then it's incremented again. So it's now 82, and then it's loaded in again. So now it's going to load in from 1314, and it's going to load in this 33 here, and then it goes up again, and this time we've loaded in a 0 here. So you can see that here, and it's done the same with the Y register here. It's got 80, 82, 84, 86 here. You can see the 33 is loaded in here. So again, it's just working in the same way with a double increment. And again, we just specify square brackets to define that. And as you can see, we can do the exact same with auto decrement. It's the exact same kind of idea. We just put the double or single minus before the register, and you can see here we are doing our auto decrements here, and we just specify the minus before and put that in square brackets, and that's all there is to it. Okay, now as well as those very useful ones. We are just going to discuss the other kind of addressing mode, program relative addressing mode. Now this is where we do commands that will work by an offset relative to the current running code. And again, I think this is probably related a little bit to that other addressing mode, this PCR, because the branching commands will of course be relative as well for relocatable code. But what a branch does is it compiles down to a relative offset. So instead of jumping to memory address 2000, it will calculate the difference between the current compiled code and 2000, and it will store that. Usually of course this will be a single byte, and this will allow us to jump a very short distance here. So let's just fire this up and let's see what happens. So here we're going to show some letters to the screen. We're going to show A and B. There's a command to show X here, but we skip over that with this branch command and we just show C. So the branch is effectively a jump to here. But the point is, as I say, it's storing an offset. So if you are relocating this code, copying it from one place to another and then running it again, well, you've not got any direct references to jump to memory address 2000 or 5000 or whatever. You've got jump to offset plus 500, which is going to be the same wherever your code ends up running. Now, in that case, you can see that's worked just fine. Now, what about if our code's very big? Because this is just a single byte value offset, and that will only jump from -128 to +127. So if we put a gap of 129 bytes in here, our code won't compile. I've now got an error, and it says error, jump distance too big. It's just off the screen down here. So we don't want to use that command if we've got very big pieces of code. But we do have an extra command on 6809 called LBRA, and let's try this out here. And that's a long branch, and that will work for any range really within the 16-bit range. And you can see here it's worked again just fine, even though we've got that large amount of memory, but the command will be bigger. So we want to stick with our regular branch if we can. Now, borrowing from the 68,000 kind of way of doing things, we do have, rather nicely, a load effective address command. Now, what this will do is it will calculate the result of the addressing mode statement we define, and it will store the resulting address in one of our registers. Now, the main reason I think you would want to do this is, you've seen all of these commands here, and some of them are a little bit complicated. You know, you got these sort of things like this. This is going to be a big command, and if you wanted to use the resulting address dozens of times, you wouldn't want to specify all of that each time because it's big memory wise and it's slow because it's big. And so what you can do is you can store the resulting calculation of that address in another register and then use that register as the pointer to that address later on. And that's what we're doing here. So LEAU will calculate the effective address of Y offset by hexadecimal 100, and it will store that result in U, not the value at that address, but the calculated address. Okay, let's fire it up and let's see what happens. Okay, so here's our example here. So we've loaded Y with hexadecimal 2000 here. You can see that there. And then we've loaded in U from Y offset by 100. Well, Y was 2000 and U has now got the value 2100 because it's stored the result of that calculation. So if we did an LDA of this value here, that would have loaded in from the address Y offset by 100, effectively 2100. But rather than loading in from that address, what we've done here is we've calculated that address and stored it in the U register, so we can now use that U register in various other places in our code if we need to use it multiple times. Now in that first example, we've loaded in from Y offset by 100, but we can do this with other registers as well. For example, we can do here, we've loaded in X from Y minus minus here. So you can see here that Y has gone down by 2 because of the double minus, and that address has now been stored in X here as well. And here we've loaded in S, the stack pointer. We can do that as well, and we've loaded in that from the indirect address at hexadecimal 80. So at hexadecimal 80 is 1112, so you can see the stack pointer has been pointed to that now, but that could cause our code some problems because that's the stack pointer that handles our jumps and things. So anyway, there we go. We've gone over an awful lot of addressing modes here because the 6809 has an awful lot of them. I hope you've found this interesting. What I'd suggest you do is if you go to my website, you can download the build scripts I've used today and the source code, and you should try these out for yourself. Try different values with them and just see how they work, because that's really how you get used to these. You can't really learn these just by seeing a video like this. You need to sort of fully play around with them and use them in your own examples before you really properly get to grips with them. Of course, there's also the documentation on my website, which you can see here on screen, and hopefully that'll help you out as well. Anyway, please take a look at these, and I hope you'll find them interesting. Of course, as things progress, you will find you'll start to get very used to some of them, and personally I only have used most of these just for this example today. They're not things that I've needed in my little programs that I've written in 6.809, so don't worry about it if you're finding some of them daunting. You'll probably just need to know them so you can read other people's code. You won't necessarily need them in your own programs, because as long as you know a way of making the things you need to do work, you can use simpler methods that aren't necessarily the most efficient. Anyway, I hope you've liked this. I hope you found it interesting. If you have, please like and subscribe, because that really helps me out. Of course, we're going to be doing lots more 6.809 videos in the future, so hopefully you'll stick around for those, and we'll be looking at some of the 6.809 machines, the platforms themselves, later on as well. Anyway, I wish you all the best with the programming. I hope you have lots of fun programming 6.809. Thanks for watching today, and goodbye.